Yeah. But he did some analysis of the your competition results, and this was not strictly a competition, but we did have we basically ran people on 16 by 16, and I think we eliminated half, and then we ran them on 64 by 64, then 128 by 128. And at the end, there were some clear sort of front runners. Then we actually ran them on 256 by 256, which is getting pretty large. And these are the top. This is our TA. I didn't make him work too hard on this, so these people all beat him. So yeah, I thought it would be interesting to hear from a few of these people about what they found actually made a difference. Because this is actually a fairly big problem if you think about it. You're not quite up to 100,000 states, but it's you're actually solving something that's close to 100,000 states to a fairly small degree of accuracy to optimality. So I'm not sure what the scalability is here. So I've had one team send me some slides, and the others maybe they can show us on the board roughly what they did. Yeah, sometimes just very small little changes can make a big deal. But I guess the first so I guess let's see if we look at these results again. So Dow, Jeremy, I guess he was the winner, we'll say, so we should clap for him. Especially, wow, he was scaling really well. So that was pretty impressive. And it's a pretty simple program, I think, as well. So you can tell us about that. We did. So these were all with 4 processors or 4 workers. We did a few experiments with more workers. I guess this is the performance, but the scalability results were a little strange. Still trying to figure this out, but so he was apparently maxing out the number of cores, and then going from 1 worker to 2 worker, 4, 8, 16, 24, and we see 1 worker. I guess we would assume that in most cases that's going to be equivalent to just non-distributed, unless something in the code is using multiple workers, even when the input says to use 1. We see there's a big drop when you go to 4. It's not a drop, so this code was not actually using distributed computation. It was using matrices, just matrices. But everywhere else you see a big drop, and then there's not really too big of a drop going to 8, 16, and then you start to increase in some cases. Like this is a weird case here. So yeah, I think it will be interesting to sort of dig into this, because I think there's some low-hanging fruit for another round of improvements once we understand why, for example, things like this happen and why we can't seem to get much more speed up. So I think we could get a pretty fast version here. So since we have a presentation from these two, maybe we can have them go first, and then the others can kind of do deltas from that if they can, or they can just write things on the board. So yeah, take the floor. And talk over here so we can hear you. This is my microphone.
Alrighty. Well, you were the one who covered this. Why don't you start that?
Okay. Basically, parallel programming needs waiting. It's just an inherent part of how it works. And there's uncertainty in timing. There's the basic limitations of how our hardware works. We're basically at the mercy of the scheduler. We don't know when our threads are going to be scheduled next. And this basically introduces the need to wait and just a lot of waiting in general. So the fewer opportunities, the fewer times we force ourselves to wait, the better, generally speaking, right? And
Alrighty. Sorry. So there were kind of three primary things that we did as our optimizations. So one of the things that we did was each thread, rather than being deleted and then starting a new one, that honestly was just...
okay, then if you're going to talk about that, we can go forward to
Sorry.
like, do you want, like,
You
can I? Okay. So basically, we know some problems. For instance, there are threads that are passing futures to other threads that would wait on them to get the data and then pass futures to that data to other people, which wouldn't make much sense. Futures are just object IDs. It's just a different term for that. I'm not sure. It's a different parlance. And so this is the basic dependencies that we have for value iteration. We got an error. We need to do the value iteration first to get the error. And of course, it relies upon the previous iteration in order to figure it out. But we're already basically guaranteed that data because, in order for iteration n+1 to happen, iteration n will happen. And this is how the original parallel program handles it by default. So first, you got your main thread, makes a server thread. Then each iteration, it spins up worker threads. The worker threads then get the values, process it, bring it back to the server, and then the main thread waits on these values, and then only after that does it get the error from the server. We noticed some issues with this because this means that basically every time you're making threads, and now this gets to Richard's point over here.
So yeah, there's no reason to delete threads and then remake them. The threads exist, you can throw new processes onto them, and just deleting and recreating them takes more time, takes more resources. We just recycle them. There's no reason not to. It's just kind of a, like you said, low-hanging fruit. So the next thing is letting the threads just kind of have ownership of their own values. Basically letting them keep a hold of everything means that you don't need to constantly pass data between them, which basically causes more wait time. Passing a piece of data to another thread is also just pretty inefficient in terms of how parallel systems tend to work. And then the last bit that we have was basically what he calls speculative future dispatch, which I'm going to let you explain that one.
Basically, this is the basic dependency structure we got here. We got a set of value iterations. Each future one depends on the previous one. We got a set of errors. Each one depends on its current one. The idea is that whenever we dispatch a future, it is out in the ether and it's ready to be processed. And as soon as its dependencies are resolved, it'll eventually be processed, right? And so the idea is there's some value b for which we will dispatch value and error futures, but we will not wait on them until we reach iteration b, at which point we wait on error 1. And then after the next iteration, error 2. And so what that basically means is that by the time we start waiting on error 1, it's probably already calculated, and we can just grab that. Which basically, and at the end we'll have some trailing errors that we don't need to wait upon. We're just waiting until we get an error that satisfies our requirements, and then we just exit, and Ray cleans up all the rest of the threads. Oh, did that clip it off? Oh, gosh darn it. Okay, whatever. So as for processing time, it's pretty simple. Let's say that for every iteration, we've got a processing time equivalent to processing for one value iteration plus one error iteration. The overall time is startup time plus iterations times processing time plus what I call gap time. That's just the sum total number of wait time that you have to do. And for our initial iteration, as per the diagram I showed you previously, you got to wait 5 times. Now, these waits are going to probably be of different, actual durations, but let's just say there's an average wait time just to make this math simple. With our optimized one, where we have our owners controlling their own values and we're actually keeping them iteration to iteration, that brings it down to 3 wait times worth. And then for our speculative one, it's 1 wait time plus the maximum of either 0 or 2 wait times minus 2 processing time. times B. And so what this basically means is that so long as the amount of processing time, as long as the value of processing time times buffer is greater than or equal to 2 wait times, we have an effective gap time for each iteration of 1 wait, which means that we save, that's actually inaccurate. That should be 4 times TW times I. I must have, anyway, this is 4. And of course, we've got our trailing processes, and that technically it adds an overall processor load. It's not adding to the time to the answer. We'll be answering early, but there is this extra processor load that we add onto the server that it kind of has to clean up. But this is a worst case. Most of the time, you're going to exit out, and it's going to kill all these threads before it actually fully executes everything. But even then, you don't really need a very large buffer value in order for this to work. And especially when we're working with hundreds of iterations, you're saving a lot more time in the long run.
Alrighty, so last thing that we didn't manage to implement in time, but is kind of just another good idea and relatively low-hanging fruit. So since it's a Markov system, that means that each one of these blocks in the grid is only dependent on the ones that are adjacent to it. So if you schedule everything such that one process handles, say, this block, one handles this block, one handles this block, etc., that means that the one processing this never has to wait on more than processing the ones directly below it, which means that even if you're waiting on a whole bunch of stuff, these 4 can start processing. If this one blocks, these 3 can still process, etc., which means that you're just reducing wait time overall. Anything you want to add?
That might be about it. I think our next slide is the thank you slide. Thank you.
That last point was that's actually worth thinking about, because I mean, in the general case, doing some analysis to figure this out it's not as trivial, because you might not have a nice grid structure, but there is often structure there. People have actually there's actually papers out there on finding topological structure in these these matrices that you can use to exploit. When I saw this, they were trying to do value iteration with dis and stuff when you for out of memory value iteration, and they were trying to optimize sort of the sort of moving things off of disk into memory. And yeah, so this would actually be interesting in the general case. If you're just given transitions, you'd have to do some analysis up front to find the dependencies, but it could probably save you significantly. And so the first thing you mentioned, though, removing the need to start up and kill threads is sort of like the first key thing, I guess, that Zheng Xin found. So any questions for them? Right. So I guess it's still a mystery why I think yours was sort of blowing up when we increased the number of processors.
I think what might have happened is you increase the number of workers because it splits stuff up like this, right? No, it still waits on.
It was the number of
Then
workers.
I'm not sure, actually.
Yeah, that'll be interesting to look at.
It's probably something stupid and simple.
Yeah, so something I'm sure that if we looked at it for a little bit, we would find it out. But yeah, somehow increasing the number of workers can have some overheads that interact badly. All right, so let's see. Who else was on this list that would like to talk about their stuff? Ayam and Kumar. So you can say a little bit, but you didn't actually do distribution, right?
Yeah, kind of thing. But well, you did mention that the get successors. So here's the thing: it's not totally just matrix implementation. So my idea was we're just gonna be tested on 100 by 100. So my focus was how to get the best time for this grid. So when I did this, matrix implementation was better than the actual distributed implementation, but it was a full matrix implementation. Let's say for 10,000 by 10,000 would take around 400 seconds. So that was not good. So what I did was I divided the list of states into, let's say, four batches. Then I called get successor for each state. So let's say the these states, after taking all four actions, can, let's say, end up in these eight states, right? Now, when you're doing matrix multiplication, you cannot do 4 by 8 or something like that, right? So I had to make a 8 by 8 matrix for the transition matrix and the reward action matrix, right? So basically, this was a 10,000 matrix. I couldn't divide it just by square of 4 by 4 matrices. So I had to do this thing and divide it into a little bigger matrices. It's in terms of in the same line of what his last slide was, so that we can divide a bunch of states, right? And I did that manually in a sense. Its overhead was around 8 to 9 seconds for, let's say 6 to 7 seconds for 100 by 100, right? So after I did that, just the serial implementation of this matrix multiplication could solve 100 by 100 in around 12 to 13 seconds. So yeah, that was kind of cool. So this could easily be parallelized because none of these each matrix multiplication are dependent on each other. But the silly thing was that as these things grew, right, I was sending the whole data to the server and the data back. So there was kind of an overhead that I couldn't wrap around on the data processing parts. But I think, yeah, if I marry this with some of the distributed ideas, I think it will get some more improvement. But yeah, that was my main finding. I mean, like matrix to matrix is too big to handle if you're having large enough batches, and if you can afford the overhead of making those small transition tables beforehand, you can just use that and parallelize, and the matrix multiplication will happen.
Yeah, I think that is the. So there is going to be this structure in the matrices, and that's the key thing. So yeah, it would be interesting to see if having the matrices in the individual nodes would help a lot. I mean, you get some sort of constant factor at least. I would expect. All right. So we have Chow. Is Chow here? You want to say a little bit about what you did?
So I think the main advantage is splitting up making sure you don't respawn the threads every time you manage it. But one thing I noticed is every time we ran the original class code, it would pop up with this warning that says like failed to serialize this numpy array. So I went and just Googled why is it doing that. And so apparently whenever you pass stuff into array, you have to serialize it into basically a pickle or a series of bytes and then pass it along. And it turns out they have very efficient implementations of this serialization process for certain data structures and not for others. And it may be a bug that the numpy array type that we're using just fails to serialize. But I noticed that, so I was like, well, all our values are deterministic, so why don't I just transform my array into a dictionary, since we're basically just doing a state action lookup, and then pass it along that way. So I'm not sure how much of an improvement that was, especially since we cut out this respawning of threads every time. But that was something that I was interested in looking at, was why is it failing to serialize our numpy arrays correctly? But maybe that had some impact on performance. And I think that was the only major difference that I used, was I passed along my data structures via a series of dictionaries rather than a environment class.
Okay. Then Bermilo. Yes, you want to say a little bit about what you did?
So I did something similar to what Scott did, where that serialization, Jeremy and I did kind of find that odd. Did something about that, but other than that, I just refactored the code and made it a lot more faster. So I turned all the for loops into list comprehensions, which in Python, that's actually the fastest you can get to. So that made a significant difference.
Okay. Yep. Okay. And then Jeremy, the winner, the champion.
Yeah, I did something similar to Scott did. So like when you started, you just pre-compute all the possible each state, all the possible transitions,
right.
Store it in like a list, and you do the same thing for the rewards. Because like if you look at the frozen environment code, like the reward just passes back some values of an already created array, so you just take that array.
Yeah.
And then instead of like passing it into the function every time you call the worker, I made the computation workers, like the evaluation workers, an actor instead. So you can store all of that transition and reward information, so you won't have to serialize it once, and then it should be stored on like that worker's own wavelet, and whenever it calls the value iteration method, just like looking to the data. And then I got rid of the value iteration server, because at that point it was just basically storing like just the right values. So there's no point making more than that as a local related update every time you get on the call.
Right. Yeah, that I think so. Yeah, so basically it was. I mean, it was a pretty straightforward implementation, but a few small differences from what Zheng Xian was doing. I think like he had a server for the value function, and that there's some overhead there in moving that back and forth, and you just used your main program, and and then the other thing was having these workers and just one time passing the matrix or the transition information was pretty important. Because then they're just there. You do that once, and they just iterate pretty easily. It was just at the end of every iteration, you sort of call them again. I mean, you were waiting. You had a wait loop inside your main program, and then at the end of every iteration, they have to get their new value function. But just the part of the value function, well, I guess, you were giving it all, or were you just the part they needed?
Yeah, I was giving it all.
Yeah.
I was
That would be an extra optimization, similar to the structure, finding the structure of the matrix. But that could lead to some savings as well. Maybe not as much, but if we were moving up to 1 million states, All right, so good. Well, I'm kind of curious to keep on. I may have somebody continue pushing on this a little bit, given what we've learned, because I think we could get a really fast implementation. But it was interesting to see people's different ideas for this.